Welcome, Lizzie Silver, to talk about causal discovery in Python. Causal discovery means learning what causes what from your data. That's an incredibly important thing for anyone who wants to make conclusions from their data or to use their data to develop a strategic plan for meaningful decisions for what to do next. Lizzie Silver is a senior data scientist at WSP. She has broad interest in applied data science and has worked in projects in electricity distribution, water distribution, abandoned mine shaft detection, fish ecology, and arthritis monitoring via wearable devices, among others. She did her PhD in causal discovery at Carnegie Mellon University. Her pastimes include singing in choirs and running the monthly Melbourne Machine Learning and AI meetup, as well as the Melbourne chapter of Puzzle-Fight. She'll present a review and comparison of softwares available for causal discovery in Python. First, a brief intro into causal discovery, then run through various packages intended for that purpose, and if there's time available, maybe we'll get a quick demonstration at the end. Everybody please welcome Lizzie Silver.
Thanks, Genevieve, and thank you all for being here. I have had spoilers for my first slide, which is what is causal discovery? For those unfamiliar, causal discovery is about learning what causes what. Great, you can see my cursor. So causal discovery is what you would do first before later doing causal effect estimation, that is learning how much does each feature have an effect. The input to a causal discovery algorithm is some kind of table with features in the columns and observations in the rows. The output is a graph, with each feature being one node in the graph, and there's an arrow from one feature to another if there's a causal effect. So smoking causes lung cancer, we have an arrow from smoking to lung cancer. And in between is the causal discovery algorithm, which is very complicated and can be explained in detail, but in 30 minutes, not really doable. So what I'm going to do is point you, if you want the mathematical details, to a previous talk I gave on this topic. That QR code will be on the final slide as well. And instead, I'm just going to give you some reason to believe you might want to do this, some intuition about why it might work, and then just go straight into how would you do this in Python. So when would I want to use causal discovery? Given that we've all heard that correlation's not causation, and we don't want to make mistakes, the trouble is that we have to take actions in the world, and we can't always do a randomized controlled trial to find out what causes what. It is unethical to force people to smoke and see whether it gives them lung cancer. So sometimes we have to make causal conclusions from observational data. Now, usually we'd like to rely on our background knowledge about what causes what, but unfortunately, sometimes we don't know all the causal relationships. In this case, we can add what we do know as constraints and use causal discovery to learn the rest. Sometimes our experts are not perfect and they may believe something that's not true. In this case, it might be worth just trying causal discovery and see what it gets you. You may find that the model you get out of a causal discovery algorithm actually fits the data much better than an expert guess. And the last situation is that you might just have way too many features to have any idea what's going on. If you're trying to learn a genetic regulatory network over 20,000 genes, you won't have background knowledge about which genes affect the others. In this case, causal discovery is a great way to come up with a first guess, to generate hypotheses and prioritize which experiments you're going to do first. When can't I use causal discovery? If you have measured only two things, and those two things have a Gaussian distribution, by which I mean the bell curve, the normal distribution, and they have a linear relationship between them, in that case, you're very sad. Oh, pardon me. You cannot do anything with causal discovery in this situation. That has been proven, and this is why you've heard that correlation's not causation. However, in every other case, we can learn something. For example, let's say we've only measured 2 features, but those features have a non-Gaussian distribution. So this is not the bell curve, this is a uniform distribution. In this case, if I get the direction of causation right, and it's the little tick mark, and I have the predictor x1 predicting the effect x2, then you can see the amount of noise I'm adding has got no relationship to the x1 value. But if I get the direction of causation wrong, suddenly the amount of noise depends on the value of x1 in a way that feels counterintuitive. We expect intuitively that noise is just random other stuff that's happening and should have nothing to do with the relationship between x1 and x2. So if you get the direction right, you see a change in the dependence of the noise on the cause. So that's true for the, this is a situation in which you can use linear non-Gaussian acyclic models to learn causal relationships. If you have Gaussian noise but nonlinear relationships, you can use the same kind of trick. If I get the direction of causation right, the noise is unrelated to my predictor. This is real data. This is rings on abalone predicting their length. Rings basically being a proxy for age. Age increases the length of the abalone, but length doesn't increase the age. So this is just trying to give you some intuition that it might be possible to learn causal relationships if you have data from a certain distribution. The other thing you might have is more than 2 features. On this one slide, on the right-hand side, I want to give you some feeling for why this is doable, and on the left-hand side, why it's hard. This is the observable universe, one picture. And the number of directed acyclic graphs, or causal models, with 25 features is at least 10 orders of magnitude larger than the number of atoms in the known universe. The space of models that we're trying to find the true model in is very large. That's why this is a hard problem when you have more than 2 features. However, it is doable because we have sometimes these V structures where you've got 2 things that are not causally related, but they both influence a common effect. So in this case, in this example, there's no dependence between the battery charge and the fuel tank level in a car, but they both influence whether a car starts. So they're independent. But when you condition on their common effect, let's say the car did not start, and you know that the battery is fully charged, you can learn something about the value of the fuel tank. You learn that it's empty. So what we see with these V structures is independence of the predictors, but dependence conditional on their common effect. That unusual pattern of conditional independence, of independence and conditional dependence, indicates the presence of a V structure. And when you see it in the data, you can learn that V structure exists and orient these edges in your causal model. So it's doable, but it is computationally intense. So if you're in this situation, my suggestion for which algorithm to use depends on the number of features you're trying to learn on. I will say the grasp and boss algorithm, they were invented after I graduated, so I don't really understand how they work, but I do understand they're way more accurate than anything that existed when I was studying, especially on dense graphs. So I recommend them up to maybe 100 features. After that, you want something more efficient like the PC algorithm or FGES. Other questions that influence choice of algorithm? You may believe that there are some latent confounders that you have not measured in your data set, in which case there are algorithms all based on FCI, which will represent the extra uncertainty related to those confounders. Many of these algorithms take a statistical test or a score function as a plugin, and those tests and score functions depend on whether the features are continuous or discrete or a mixture of each. When you have a mixture of continuous and discrete features, this is actually the hardest case because you need a score or a test that has similar levels of power no matter how many features are discrete or continuous. People often ask me, what about time? Doesn't time make it much more easy? It's actually much easier when you just have a snapshot of a population, because typically when people want to take time into account, it's because they've only measured one system over time. If you measure, say, Australia's economy over time, your sample size is one. There's one Australia. And you want to use the different points in time as effectively different samples, but you can have strange things happening, like different causal relationships working depending on seasonality. So time actually makes things much more difficult, and I won't talk about it further. So instead now I'm going to jump to a worked example. For this worked example, I wanted a really small data set, just 3 features where we could all agree on the causal model. So I picked the relationship between altitude, latitude, and temperature. I hope we can agree that warming up a location will not move it, but moving may change the temperature. So we can agree on these causal directions, hopefully. This data set also has some nice non-linearity and non-Gaussianity. And it has a V structure. So it should be extremely learnable. I also want to mention Tetrad. Tetrad was the first software available for causal discovery. It is a massive Java library. It has been in development since the early 90s, and it's mostly the work of Joe Ramsey, who's pictured here holding his Markov blanket, which is a joke for the real stats nerds in the audience. And it has everything. Joe is at the Carnegie Mellon University Philosophy Department, which is where I studied. And the philosophy department has realized that most data scientists use Python, so they now have not 1 but 2 Python libraries for causal discovery. The first is called causal-learn, developed in 2020, and this is part of the Carnegie Mellon University Center for Causal Learning and Reasoning. All of the implementations in causal-learn are new. They're all 100% Python. And because they're 100% Python, they have limited performance for the really large graphs. They don't have all the optimizations that are in Tetrad, but it's really actively maintained. It's got a large user community by the standards of causal discovery user communities. So I will now jump to VS Code. Oh yeah, I wanted to show you in 3D the relationship between temperature, latitude, and altitude. So this is temperature on the y-axis, latitude and altitude on the horizontal axes. And you can see that there's this sort of surface of different temperatures at different locations. So, causal-learn. Let's see, is this big enough? We'll start by importing our libraries, loading our data, and then learning a graph is just this one line. and it's really quick, and it learns the right graph. But you may have noticed a little tell here. What happens if I change this seed to 1? It picks up the relationship between latitude and temperature, but it can't orient it because it no longer has a V structure, and it's missed the altitude to temperature relationship. So if I don't set the random seed at all and just keep generating this, it flips between the two. There is some randomness in the permutation searches. I'm not exactly sure where it is. I dug around in the code and I couldn't see it. But I will say that they take a score function, and the score function that is the default is best for Gaussian data, which this is not. So I haven't exactly tried to optimize this. But yeah, that is causal-learn on this example. Second Python package, also produced by the CMU philosophy department, is py-tetrad. It's a Python wrapper for tetrad. It's got some Python API in it. It's got this tetrad search class, some dataset type translators and graph translators, and you can also access the rest of tetrad through jpipe. Given tetrad has everything, this is really powerful. It's also got a bunch of optimizations for dealing with large graphs, and all the newest algorithms get implemented in tetrad first. So yeah, it's maintained, it's got a small but dedicated user base, but it's mostly maintained by Joe, who's a Java guy, so could use some help with the Python packaging, getting it up on PyPy, things like that. How about learning that same model in py-tetrad? Once again, load up our data, and again, it's one line. It's a few lines. And in this case, I don't get a nice image out of the box, but you can read these edges are what we want. We've got the altitude to temperature edge and the latitude to temperature edge, and I can output an image of that graph, which is looking good. Good job, py-tetrad. Now, I should admit that I signed myself up for talks in order to force myself to do things that are on my to-do list. So the rest of the packages that I'm about to talk about are ones that I had intended to understand. So I put them in the abstract so that I had to review them. I really wanted to love the causal discovery toolbox. It's built by Divyan Kalainathan, who's now at Fentech. And he did his PhD in causal discovery under Isabelle Gouillon, who set up the causal pairs challenge. So it's got a real emphasis on the pairwise methods, things like the additive noise method I mentioned earlier. And it's also got some deep learning methods and other things related to using lots of features are imports from the PCalg-R package. Unfortunately, it's no longer maintained, hasn't been updated since 2022. And let's just go over that same example in CDT. Come on. There we are. Load in our data. You have to feed it a complete graph as an input. And then it learns that altitude causes latitude. So this is using the additive noise method, which if we review our data, the noise does look roughly additive depending on what point on the surface you're at, but it may be that it's just not working at a pairwise level. Because if I just look at one view of this, the noise doesn't look additive. So I'm not entirely sure why CDT is not learning the right thing, but just based on that quick evaluation, can't exactly recommend it. The next option was the CausalNex package. This one is another one built by an actual company. It's built by McKinsey's AI consulting team, Quantum Black. Not sure if it will be maintained further. Last commit was 9 months ago. And its emphasis is on learning the size of causal effects, not causal discovery, but it does have a couple of causal discovery methods, and they're gradient descent-based methods. So if you wanted to fit causal discovery into a deep learning pipeline, this would be the way to do it, except that they're not very accurate. So if I try to learn this graph, once again, using the same cities data, it outputs an HTML file, and it learns that latitude and temperature cause altitude. But I do like this clicky draggy thing. It's extremely satisfying. So I can't really recommend the gradient descent-based methods either. They're based on a relaxation of the acyclicity constraint, and they don't work very well. The last package that I put in the abstract and promised to talk about was Tigramite. And when I went and reviewed that, it turned out that it only had time series methods and was also very complicated academic code. So I will say that if you have time series data and you know what you're doing, Tigramite is the way to go, but I cannot do my 3-variable example in it. So that is basically it. That's my review of the causal discovery packages in Python, and shock, surprise, I recommend the 2 produced by my academic department. So in summary, we all know that correlation doesn't equal causation, but in some cases, under some circumstances, you can make an assumption and infer causation. Most users who want to do this in Python should use causal-learn. If you have a large set of features, like a genetic regulatory network or a niche use case, I suggest using py-tetrad instead. And if you're an expert and you have time series data, Tigramite. That is it. Thank you. Any questions?
Thanks. Apologies if this is more for your 101 talk, which I will go and watch, but what else can you do with these models? So if the outputs you showed were, finding the correct causal relationship, but then can these models then be used to predict things? Like if you get new values of these input features, can you provide estimations of whether, something is going to happen or not?
Yeah, great question. How is a causal discovery model, how is a causal model different to a statistical model? The difference is you're making predictions about what would happen if you were to intervene and change something in the world. I'm predicting that, given the smoking and yellow fingers and lung cancer example, I'm predicting that if I were to paint someone's fingers yellow, they wouldn't get lung cancer, even though there is a correlation between having yellow fingers and having lung cancer because of the nicotine stains. The causal effect is from smoking to lung cancer and smoking to having yellow fingers. So you're predicting the result of interventions. A statistical model just predicts what will happen if there are no interventions, if you're drawing from the same distribution and not intervening and changing anything. So we want to use causal models if we want to do anything in the world. Causal models are widely used in advertising because they want to know, like, what is the causal effect of showing someone this ad? Because maybe they would have gone and bought the product anyway. Does the ad actually change their propensity to buy? They're widely used in health, which is a much nicer and more fun example. I think they should be used more often in asset maintenance. Yeah, there's a lot of applications.
Thank you, everybody. Please join me again in thanking Lizzie Silver. Lizzie, we have a gift for you. Thank you so much for your talk.